Hey up! So this is going to be a little video about motor controllers and MOSFETs, half bridges, bit about capacitance, inductance, LC tank circuits, ringing over voltage, and essentially how to make a bit of circuitry to control one of these. Nice beefy motor. This one's out of a washing machine. I've actually never managed to spin it up before. And I think hopefully you'll see in a bit why. So just as a quick demonstration, I've got the motor controller that I've been working on the bench here. So actually maybe I should probably draw out what's actually going on here. So it's different types of motor controllers, but the one that sort of to me made the most sense and does seem to be used most widely is called a half bridge. So let's say you've got your input there, and this might be your battery plus and battery minus. Then that will first go to a little bit of bulk storage, capacitor, just to smooth everything out. So yeah, if there's like any quick changes in the amount of current drawn, then the voltage on the battery won't drop. It will get taken out of the capacitor instead of the battery. So you basically just use capacitors to regulate the flow of current. And when you're looking at all these, just think tubes, just think water flowing through them. So you've got water coming from up here, and also think of this as actually how high it is. So if this is like B minus, that's connected to ground. If it is, ground, that's 0 meters. Up there, that tube's up in the second or third floor. That's where we're at. Where we're there, we're 12 volts up there. That's well high. So all that water wants to trickle down, and it wants to get to B minus really, and then yeah, it wants to get to its lowest energy state basically. Same as water flowing down a hill. So yeah, so we've got water flowing down the hill from B plus, and we basically want to connect our motor. Now we're going to connect the minus of the motor to the minus of B plus, but to feed power to the motor, what we're actually going to do is put it into this half bridge. So we're going to have two switches. So this is these two switches together here make up the half bridge. And the principle is, first, if you imagine first they're both off, scenario where neither of them are on, nothing can flow through here. There's no path here. This is open and this is open, so it can't get through. Now, what we do is we turn this one on. So this one is then shorted. If we follow it through, current can now flow, and it's going to flow through the motor and back out the battery. Now, to regulate just how much power is going to the motor, what we can do is turn this one off for a bit. So now this one's open again and current can't flow. However, this motor is already spinning up, and it has something called inductance. Now, there's a lot of things flying about at the moment. We've already had capacitors. The next thing is inductors. And the way you have to think about inductors are, imagine spinning up a merry-go-round. So it takes a while to give it a push to get it spinning, but once it's spinning, you're not just going to grab onto it and stop it from spinning. If you're going to try and do that, it's going to rip you with it. It's got too much speed. So An inductor is something that doesn't like change in flow. It'll go with it once you speed it up. Once the charge is flowing through it, it's like, yep, keep it coming. But if you just suddenly try and stop the charge flow, it's like, no, keep it coming, and it will just pull it with it. So you've charged this guy up, you've let current flow through here, and then you suddenly turn this off. Well, it's going to try and pull that current from somewhere, and if needs be, it's going to trash this guy to get it. So what we do instead, when we turn this one off, so this one's open again, we close this one, so there's once again a loop. And this guy's happy. There's no, you can still keep the current going at the same speed, same rate of flow basically. But yeah, but as the motor slowly uses up that current flow gets smaller and smaller. So then once again, down to a level where it's small enough, we open this guy again and we close this guy, and then boom, we can charge it up again. So you got to think of it as like every time we open this one and close this one, we're letting current flow, and we're pushing the merry-go-round. We're letting it speed up again, and then when we close this one and open this one, we allow it to just freewheel on its own. Now, very important thing, these two can never be open or closed at the same time. They're both on at the same time, and current can flow through here and through here. It's just going to shoot through, and it's most likely going to burn both of them out, and whatever else is in the way. If the battery can provide the power to burn stuff, it will. So whatever happens, these two must never be on at the same time. So we know that we can roughly control the current in here by flipping these on and off exactly how we want them. So we need a smart way of controlling these two switches. And nowadays, best way of doing that is something called a microcontroller. Now, if you're into electronics at all, you'll have heard about these Arduinos. You can get these off eBay. They're basically, if you see there's a little USB plug there. You plug them into your computer, you program in some code, and it will just repeat that code. So that code could be check for how fast the user wants the motor to spin, and then toggle these guys and apply the right switch them in a way so that there's enough current going through the motor to get it up to a specific speed. So if we go on to an actual practical example of that, this is the motor controller that I designed about 2 years ago, but it's got some issues with it. So remember I was saying about this inductor. It's like the merry-go-round. You can spin it up, but once it's spinning, you can't just let its you can't just try and grab onto it to slow it down. It's gonna pull you with it. And there's actually, if you put an inductor in parallel with a capacitor, you get this weird effect where if you apply a voltage across here at the right frequency, you will get the capacitor charging through this way, and then it will charge the other way, and it will you get a sort of like springy sort of like ringing, and it will just it basically start oscillating. Oh, I just realised, oh shit, shoddy camera work here. But yeah, you can basically create oscillation between the two. So as the capacitor discharges through an inductor, the inductor's like, oh, right then, okay, we'll start spinning. And yeah, allows the current to go through. But once the capacitor's empty, there's nothing more to give there. The inductor's like, what, fuck, well, I want to keep pushing. So it tries to, but there's nothing there. So the capacitor will charge up even more than normally would on the other side until all the charge is on this side. And once it's all on there and the inductor can't push anymore, the capacitor's going to push back. And then the inductor's like, alright, slows down, and then pushes in the other direction until all the charge is on this side again. And then it keeps repeating. So charge builds up all the way on this way, starts going this way, inductor's like, alright, we're going that way now, until all the charge is on that side, so it can't pull anymore. And once it's there, inductor's like, alright, okay, we'll go that way. And then it all goes there again, and it goes onto that side. But yeah, so only reason I'm explaining this is because you can get some weird unwanted oscillations out of this, and I'm going to show you now why they can be pretty bad. So starters, going back to the motor controller, basic setup is we've got a computer power supply feeding 12 volts into the B plus, B minus. Then we've got our capacitors here to smooth everything out a little bit. And then we've got our first switch, which will be this one. And then we've got our second switch there, which will be that one. And then the motor's connected there. So yeah, same thing, 12 volt in, battery, high side switch, low side switch, inductor and motor. And in this case, the inductor is actually in the motor. The motor itself has inductance because it's just a bunch of coils of wire. So yeah, if I now turn this on, oh yeah, and I've got the ammeter in series with the motor and the power supply. I've got that on the negative, so I'm basically reading the return current from the motor controller back to the power supply. So we can see at the moment idle current is 0.04 amps, so 40 milliamps. And yeah, if I connect this up, see the motor starts spinning. And then I've got a little potentiometer here, which acts as a voltage divider, which is another thing. But essentially what I can do, as I turn this, you can probably hear the motor spinning more. Oh, but and I pulled too much power, so I'll quickly reset the power. Alright, so yeah, if we keep an eye on the current, so we're already at below an amp at minimum. We start winding that up, we're up to 1 amp, 1.5, 2. And the thing is, it's not really the current, it's not really the current that the motor's using as it's going along. It's the current the motor needs to speed up to the speed. That's where you get the big spikes. You see there, it briefly went up to 5 amps. There's 7. So yeah. Oh, what am I? Oh, there we go. So what's actually controlling this? So where I said I've got the smart up bits here, the microcontroller, switching these on and off. That's what we're seeing on the screen here. So when the when the high side's on, the low side's off. When the low side's on, the high side's off. And by turning the pot, we're just changing the amount on compared to not on. So, and we would refer to that as the duty cycle. So how long it's spent on compared to how long it's spent off. you can see there it was essentially fully on. Oh, okay. So why is the main reason I'm showing you this, guys? Well, general interest as well. I don't know if anyone, if this piques anyone, if they've got any more, if anyone wants to do this as well. There's so many resources online, but it can be sometimes a little bit daunting. So if anyone's got any questions, I'm smelling. Oh shit, getting some arc in there. I was wondering why it was spinning a bit quiet. Oh, that's getting warm. I might turn that off actually. Oh, yeah, everything's getting a bit toasty. Okay, so now if we, actually I need to turn it back on one more time. See, you can kind of see here, we're not just getting nice on or off. We're getting some bits going on here. That's going. So if I zoom in on that, we keep zooming in. What we see is that it's oscillating. It goes up, and it goes down, and it goes up, and it goes down, and it goes up, and then it's like a spring, sort of like bouncing up, and then as it's bouncing, it's losing energy until it gets to a steady state. That is this tank circuit. It's charging up, and it's charging the other way. It's charging up, and then until it gets to the end. So imagine it's like when you first turn it on, it's like whoa, 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 and then it settles in the middle. Oh, I didn't miss that. So you first turn it on, and the charge goes, and then it settles and it's happy, and that's what it's doing here. So it massively overshoots, and it undershoots, overshoot until finally it comes to the resting position. Now, this wouldn't really be an issue, because if we zoom out in the timescale at the moment, like this is one of these squares at the moment is 100 nanoseconds. So if I zoom out further, like this spike is happening within a millionth of a second. However, it is over twice the height that we want it to be. So we want that to be off the top of my head, I think that's meant to be at 24 volts. At 12 volts, and instead we're going up to over double, so 24 volts. Again, with this 12-hour supply, and these MOSFETs, these switches rated for 40 volts, that's fine. But if I want to use, let's say, a 36 volt supply, which these 40 volt MOSFETs should be fine with, then 2 times 36, I'm going to be seeing 72 volt spikes on there. And when I first turned this thing on, it would work for 2 minutes and then die, because that's exactly what was happening. I was getting spikes that were way over the maximum rating of the switches, and when the voltage is high enough, it doesn't really care what's in between the middle. Like you've seen lightning, like miles of air, and it's just like, I'm going to go that way. And it does. So, and it'll burn anything on the way and destroy what's in the way. So I burnt out a few components. So until I figured out, lower the voltage. You got those spikes. You got to zoom in on them. And yeah, there's some ringing there. So in my sort of like quest to figure out what's been causing this ringing, I've had loads of people say, oh yeah, well it's definitely parasitic capacitance and inductance, and you've got some sort of ringing going on, and the only way to do that is to dampen it. So if you've got an underdamped circuit like that, it's gonna oscillate massively. So if you damp it with a resistor, it won't oscillate as much. but you add a resistor in, time it takes to charge up slows down, and yeah, I'll try and throw some graphics over this. But yeah, so the only real way to do it is to get everything really tight together. Like, you want the loop area between the gate of the switch and the source of the switch to be as small as possible. So from the gate to the source has got to be as small as possible. So I'm thinking, all right, I'll try some sort of double-sided PCB where I have the MOSFET switches on one side and then the gate on the other side. Now, this is a milled PCB. There's a bridge somewhere in there, and I haven't found it yet. But it's also, yeah, it's just another pathfinder. So this, I don't know yet if this is going to work, but I've come across something which is going to solve all of that, which is a MOSFET that has the driver within the same package. So you physically can't really get it much closer together. So fingers crossed. We won't be blowing up any more components, and we'll be able to deliver a crap load of power and go from little dinky motors like this one up to bigger boys like this one, and in the future much larger. So yeah, we'll see how that goes. But yeah, next bit I'm just going to start designing this next version 4 controller. I think I'm going to film some bits here and there, try and do some screen captures as well of especially like using the software, so PCB or circuit design, the schematic capture, the PCB layout. I'll maybe do a bit about ordering as well, or sourcing components, and yeah, I think I'm going to start doing some projects here and there and just film them for myself, for anyone who's interested, and yeah, if anyone's got any ideas, let me know. Cool. Bye.